Hello, welcome. Today we're going to be looking at some calculations in transport phenomena. Mostly in transport phenomena, you're going to be calculating flow rates. And when you're calculating flow rates, you're going to be given velocity distribution expression. And you are now going to be told to calculate the flow rate Q using such an expression. You find out that the most difficult thing or the very important thing that you need to do in order for you to start solving or start deriving or start proving an equation is for you to make an expression that relates flow rate to velocity distribution expression. And most times it's always Q equal to integral of the velocity expression times area, or sometimes volume. So that's what we're going to be looking at today. I'm going to be starting with a specific example. So this is the expression that I'm talking about. Q, flow rate, is always equal to integral of the velocity expression times the differential of the area. So we're going to be starting with this. Velocity can be interpreted as the volumetric flux. So velocity can always be interpreted as volumetric flux, which is expressed in terms of cubic meter over meter squared seconds. Therefore, volumetric flow rate can always be calculated. Volumetric flow rate can always be calculated by the integration of the velocity distribution over the cross-sectional area that is perpendicular to the flow direction. Consider the flow of a very viscous fluid in space between two concentric spheres. This is a sphere and this is another sphere between two concentric spheres. Whenever you hear that word concentric, it simply means that the two spheres have the same center. So this is the center of this sphere and this is also the center of this other sphere. And that's how we'll talk about the big R, this is the big R, which is the radius of the bigger sphere. And we also have KR, which is the radius of the smaller sphere. And we also pick another R in between the two. So consider the flow of a viscous fluid in the space between two concentric spheres. So the fluid are actually moving here, is entering through here, move here, and come out here. As shown in the figure, the velocity distribution is given by Bird et al. Bird et al. It's somebody that actually gave this expression. And he gave it as V theta is equal to D. This is the expression. R dot P all over 2 mu E epsilon sine theta into 1 minus small r over big R plus K into bracket 1 minus big R over small r, where E epsilon is equal to ln 1 plus cos epsilon all over 1 minus cos epsilon. Now you are told to calculate the volumetric flow flux Q. That is what you are told to calculate. So very simply, you're going to do the differential of this velocity expression that you already given. So in place of B theta, put this, and in place of the A, that's where the problem is. So how do you know the A to use? Whenever you're taking the coordinate solution, depending on the cross-sectional area considered, very, very important. So if you're taking it in theta direction, which is what we are going to be using, the A is going to be r sine theta dr d phi. If you're taking it in the phi direction, it's going to be r dr d phi. If you're taking it in the arrow direction, it's going to be r squared, that's big R squared, sine theta d theta d phi. Very, very important. You need to look at these three expressions. What the A is. The A could be this, it could be this, and it could be this, depending on the direction that you're taking. So if you look at it critically, this is how I want you to, the technique I would like you to use in memorizing this. Can you see for theta direction, we have the r d phi. These two are different from theta. For phi direction, you have the r d theta. The r d theta. Please, this should be an error. I'm not sure, but I think this should be theta. Why? Because we are having phi direction, so it should be different from, it should be the r and the theta. Whereas here that is r direction, it should be the theta, the phi. So the direction is actually, you make sure that the d's you're having at the back is not connected with the direction you're looking at. So since you're looking at theta direction, which is what we're going to be considering here, we have the r, the phi. Now, we have r sine theta here, whereas here in phi direction you have only r, and in r direction you have r squared sine theta. R direction, big R squared sine theta. Theta direction, r sine theta, whereas phi direction you have, there is no sine. So very, very importantly, you need to know how you go about this, so that you can always know that the A is equal to r sine theta, the r, the phi. So using this equation, in place of v theta, we'll put this expression. Then in place of the A, we'll put this very expression. The A equal to r sine theta, the r, the phi. So once we put it here, we can now be able to solve down by taking the integrals at the proper limits, and that's what we're going to be doing in the next video that you're going to be seeing. We're going to be taking all the problems that we have in transport phenomena, solving them one by one. You look at me the way I will do this derivation, very, very well explained, so that you can pick up. Thank you. If you like this video, click on the subscribe button. Thank you. God bless. No, don't stop.